In this section, we're going to talk about vector arithmetic. And this is one of the really big distinguishers between vectors and points. With points, we really can't do vector arithmetic in the same way. With vectors, we can do arithmetic, and it has a very useful geometric interpretation. So we're going to start with vector addition. Now, there's going to be two components to these arithmetic operations. There's going to be the actual algebraic way we compute the arithmetic, and you'll see that that's pretty straightforward. Computing vector arithmetic is easy to do. Far more important is the geometric interpretation of those arithmetic operations. All right, so let's start with vector addition. And I find it helpful to have kind of a concrete example of vectors in mind. I like to think of vectors as a change in position. So say I start from one position and I go to some other position. Okay? The vector pointing from my start point to my end point represents the net change in position. Okay? We'll call that vector v. Now say I continue my little path here. I go from where I end up at the tip of vector v, and I keep on walking till I get to this point right here. I could represent that change in position with another vector. Let's call it vector u. And so I have two vectors representing two changes in position, two motions. Now, if I put them together, notice there is a net change. I started from here at the very beginning. At the very end, I ended right here. The vector pointing from my very beginning to my very end, that vector we define as the sum of the two vectors. Okay? Notice that geometrically, if you're going to represent this geometrically, it's very important that you draw the diagram correctly. We can draw the first vector wherever we want, but when we draw the second vector, the tail of the second vector has to be at the tip of the first vector. When we draw two vectors this way, we say that we've drawn them tip to tail. So I've drawn v and u tip to tail because the tip of vector v and the tail of vector u are at the same position. Okay? In particular, note I haven't drawn both vectors in standard position, right? Maybe vector v is in standard position if I were to draw the axes. Okay, maybe vector v is in standard position, but vector u is not in standard position. The tail of vector u is at the tip of vector v. But with it drawn this way, we have this interpretation, this geometric interpretation, that the sum of the vectors v and u represent the net change in the position. Okay? All right, so that's the geometric interpretation of vector addition. Let's get a concrete example so we can understand how to actually compute vector addition. So let's let vector v be the vector 2, 5. And let's let vector u be vector 3, 1. Let's find the component representation of the sum. Okay, so to do this, I'm going to sketch out the vectors. Let's give myself plenty of room here. 1, 2, 3, 4, 5, 6, 7 on the y-axis. 1, 2, 3, 4, 5, 6, 7 on the x-axis. Okay, so I'm going to start by drawing vector v in standard position. So 2, 5, so 1, 2 over on the x, and then 1, 2, 3, 4, 5 up on the y. So there's vector v. And now vector u, I'm going to draw tip to tail with vector v. So the tail of vector u will be at the tip of vector v. Vector u is 3, 1. So from the tip of vector v, I go 1, 2, 3 units in the x direction, 1 unit up. And I have vector u. Okay? And so vector v plus u should be this one right here. Okay? And notice vector v plus u is drawn in standard position with its tail at the origin. So the tip of vector v plus u should be the components of the vector. Okay? So we could easily compute that. So the x component is 1, 2, 3, 4, 5 over. And the y component here is 1, 2, 3, 4, 5, 6. Okay? So drawing it out, we see that v plus u is equal to the vector with components 5, 6. But if we think about this a little bit, we realize that that kind of makes sense, and we didn't need to do all that work to do the computation, okay? Because we could kind of break this down into if we look at the x and y components of each of these vectors, okay, and kind of break down their motions that way. Notice that the total change in x is how far I change in the x direction with my v vector, and how much I change in the x direction with my u vector, right? If I take this and take this together and put them together, that's my total change in x. So all I have to do is add the x components. So I moved 2 units in the x direction when I had my vector v motion. And then I had 3 more units. I moved 3 more units in the x direction when I had my u motion. Okay? So 2 plus 3 is 5. Makes sense. Okay? And similarly, if I just focus on the y motion, for vector v, I moved 5 units, and then when I had my vector u motion, my net change in the y direction was 1 unit. So 5 units when I moved with vector v, plus 1 unit when I moved with vector u, gives me 6 units total. Okay? Now here I've drawn the picture in 2 dimensions because that's where it's easiest to draw it. But this principle holds for any number of dimensions. And so we can define the algebraic, how we algebraically compute vector arithmetic as follows. Let v equal v1, v2, all the way to vn. So it has n components. And let u be similar. Let it have n components, u1, u2, all the way to un. So these would both be n-dimensional vectors, so they would live in Rn. Then we define v plus u. To compute this, we just add the corresponding components. So the first component of v gets added to the first component of vector u. The second component of vector v gets added to the second component of vector u, and so on. Okay? So actually doing vector addition, again, very easy. You're just doing normal addition. You're just doing it several times, right? However many components you have of the vector, that's how many times you need to do the addition. Again, the most important idea here is not how you do the vector addition. That's easy. Make sure you have the geometric interpretation of what that vector addition means. Okay? It means that net change. And by the way, the order here doesn't matter. Here I've drawn it. We're moving in the direction of vector v first and then the direction of vector u. But if I swap it, and hopefully I have enough room here. So let's see, I went 1, 2, 3, 4, 5, 6 units down. And then 2 over. 1, 2, 3, 4, 5, 6. So if I first went in the direction of vector u, and then went in the direction of vector v, I end up at the same spot. I'm taking a different path to get there, but I end up at the same spot. So v plus u is going to be the same as u plus v because the net change from where I start to where I end is the same, okay? So geometrically, that's what we get there. Algebraically, it's easy to see why that would be true because we know that if we're just adding numbers, v1 plus u1 is the same as u1 plus v1. So for that first component, I can change it no problem. Same is true for the second component. Okay. Now, this may seem obvious. We're used to addition. We're used to when we add two things, if we swap them around, it's the same addition. But notice these aren't the things that we're usually dealing with. We're usually adding numbers together. V and u are vectors, not numbers. So when we add them, we don't mean the usual addition here. We're not just adding numbers together. And so properties that we're used to, like the commutativity of addition, that v plus u and u plus v give us the same thing, we have to be very careful with properties like that, because with this new addition, with these new structures, that property might not hold. In this case, it does. But generally, if you have a property that works with normal addition with just plain numbers, you need to be careful and double check that that property still works when you're adding vectors, because vectors aren't numbers, so the same properties may not hold.